Hello everyone, this is your Brian Orlasan Cordova. So our topic today is limits involving infinity. So we have the limits at infinity. So the limit of f of x as x approaches to positive infinity is equal to a certain number L, or the limit of the function as x approaches negative infinity is equal to a value L. So the graph of the function f approaches a finite number L as the value of x approaches to positive infinity or minus infinity. Example, so the limit of 1 over x as x approaches to positive and negative infinity. So it is the graph of the hyperbola, which is symmetric on the origin. So we're going to find the value of the function y is equal to 1 over x as x approaches negative infinity. So the value is approaching y is equal to 0. And as x approaches positive infinity, the value of the function approaches also the value 0. So on both sides, the limit of the function as x approaches from the positive and negative infinity is equal to 0. So all the limit laws are true when we replace the limit of x approaches c by the limit of x approaches to infinity, or the limit as x approaches negative infinity. That is, the variable x may approach a finite number c or approaches positive or negative infinity. Limits at infinity of rational functions. To determine the limit of a rational function as x approaches positive or negative infinity, we first divide the numerator and the denominator by the highest power of the variable x. The result then depends on the degrees of the polynomials involved. Example, number 1, finding the limit of 5x squared plus 8x minus 3 all over 3x squared plus 2 as x approaches positive infinity. So as we divide the numerator and denominator by the highest degree, x squared, we are going to divide each terms of both numerator and denominator by x squared. So we have 5x squared divided by x squared, we have only 5. We can cancel x squared since it is the highest power of x. And as we divide 8x over x squared, what remains is the denominator of x. Then minus 3 over x squared. And in the denominator, we can cancel x squared, and the constant term 2 will be divided by the highest power of x, which is x squared. So as x approaches to infinity, each term that has a constant numerator and a denominator with a variable, as x becomes larger, the whole term becomes 0. So each term with the denominator with a variable approaches 0 as x becomes larger. Taking the limit, we only have 5 plus 0 minus 0 over 3 plus 0, and it is 5 over 3. Another example, finding the limit of 11x plus 2 all over 2x cubed minus 1 as x approaches to negative infinity. So here our highest power of the variable x is x cubed. So we will divide all terms on the numerator and denominator by x cubed. So we have 11 over x squared, since 11x over x cubed is 11 over x squared. Then 2 over x cubed. Then we can cancel x cubed from 2x cubed minus 1 over x cubed. And again, all terms with a variable in the denominator approaches 0 as x approaches negative infinity. So we have 0 plus 0 over 2 minus 0. So since the numerator is 0 and the denominator is a whole number, this is equal to 0. So the limit of function 11x plus 2 over 2x cubed minus 1 is 0 as x approaches negative infinity. Horizontal asymptotes. The line y is equal to b is a horizontal asymptote of the graph of a function y is equal to f of x if either the limit of the function is equal to b as x approaches positive infinity or negative infinity. So, example, find the horizontal asymptote of the graph of f of x is equal to x cubed plus 2 all over absolute value of x cubed plus 1. Since we have an absolute value here, so we are going to look at the behavior of the function from both negative and positive x. We are going to evaluate this function from for x is greater than or equal to 0 and for x is less than 0. So since for positive x, the absolute value does not affect the function, so we can remove the absolute value here and evaluate the limit of the function as x approaches infinity. Now, since our highest degree of the variable is cube, so we can divide each terms by x cubed. We have x cubed over x cubed is 1 plus 2 over x cubed. And cancel out, we have 1 plus 1 over x cubed. And again, we have this one approaches 0. This one also approaches 0. So we have 1 over 1, which is equal to 1. For negative x, or x less than 0, the absolute value of x is equal to negative of x, where x is a negative value. Then taking the limits as x approaches negative infinity, we divide all terms on the numerator and denominator by x cubed. We have 1 plus 2 over x cubed all over negative 1. Since it is in cube, this is still negative. So we have negative 1 plus 1 over x cubed. Then we have this approaches to 0 as the limit approaches negative infinity. So we have 1 over negative 1, we have negative 1. So for positive x, our horizontal asymptote is equal to 1. And for the negative x, we have y is equal to negative 1. So on the negative x side, the horizontal asymptote is y is equal to negative 1. And on the positive x-axis, we have the horizontal asymptote y is equal to 1. You can see that the graph crosses y is equal to negative 1 on the positive side, since it is not the horizontal asymptote on the positive side. Then we have the infinite limits. So the limit of f of x as x approaches c is equal to positive infinity, or the limit of the function as x approaches c is equal to negative infinity. So the graph of the function f approaches infinity or minus infinity as the value of x approaches to finite number c. So example, we have the limit of 1 over x as x approaches 0 from the left, and the limit of 1 over x as x approaches 0 from the right. If x approaches 0 from the left, so the value of the function goes to negative infinity. And as x approaches 0 from the right, the value of the function approaches positive infinity. Now we have the vertical asymptote. A line x is equal to a is the vertical asymptote of the graph of the function y is equal to f of x if either the limit of the function as x approaches a from the right is equal to negative or positive infinity, or the limit of the function as x approaches a from the left is also equal to positive or negative infinity. Example, since the limit of 1 over x as x approaches 0 from the left is negative infinity, and the limit of 1 over x as x approaches 0 from the right is positive infinity, therefore the vertical asymptote of y is equal to 1 over x is equal to x is equal to 0. So example, find the horizontal and vertical asymptotes of the curve y is equal to x plus 3 over x plus 2. And graph the function. It is a hyperbola. So solution. So we are interested in the behavior of the function as x approaches positive or negative infinity for the horizontal asymptote, and its behavior as x approaches negative 2, where the denominator is 0 for the vertical asymptote. So we can transform the rational function into a polynomial function with the remainder by dividing x plus 2 into x plus 3. So using the long division of the polynomial functions, we have x plus 3 divided by x plus 2. So x divided by x, we have 1. 1 times x plus 2, we have x plus 2. Then subtracting this, we have x minus x, we have 0. And 3 minus 2, we have 1. Therefore, our new function would become 1 plus the remainder 1 over x plus 2. So as x approaches positive and negative infinity, function approaches the value of 1. Thus, the horizontal asymptote is the line y is equal to 1. And as x approaches negative 2, y approaches positive or negative infinity. Thus, the vertical asymptote is the line x is equal to negative 2. And we have oblique asymptote. If the degree of the numerator of the rational function is 1 greater than the degree of the denominator, the graph has an oblique or slant line asymptote. So we are going to find an equation for the asymptote by dividing numerator by the denominator to express the function as a linear function plus a remainder that goes to 0 as x approaches positive or negative infinity. Example, find the oblique asymptote of the graph of f of x is equal to x squared minus 3 all over 2x minus 4. We are interested in the behavior of the function as x approaches positive or negative infinity. So we divide 2x minus 4 into x squared minus 3. Performing the long division of polynomials, x squared minus 3 divided by 2x minus 4. X squared divided by 2x is x over 2. Then x over 2 times 2x minus 4, we have x squared minus 2x. Then subtracting from the x squared minus 3, we have 2x minus 3. And 2x divided by 2x is equal to 1. Now multiplying 1 by the divisor, we have 1 times 2x minus 4, we have 2x minus 4. Then subtracting again, 2x minus 2x is equal to 0. Then 3 minus negative 4 is positive 1. So we have a remainder 1. So the answer is a linear function with a remainder 1. So the original function can be now transformed into a linear function g of x, which is x over 2 plus 1, plus a remainder of 1 over 2x minus 4, where it approaches 0 as x approaches positive and negative infinity. So this is the graph of the function y is equal to x squared minus 3 over 2x minus 4, which can be now transformed into a linear function, which is the equation of the oblique asymptote. Y is equal to x over 2 plus 1, and the remainder is the vertical distance between the curve and the oblique asymptote. And it goes to 0 as x approaches infinity to both sides. And that's all. See you next lesson.